Hi, welcome to my channel. You are watching University of Universe. The Betelgeuse is no ordinary star. This red supergiant, located in the constellation Orion, lies only about 650 light-years away from our solar system. It's the second largest and 10th brightest star in the night sky, aside from the Sun. A few years ago, Betelgeuse made headlines when this bright supergiant unexpectedly dimmed, sparking speculation about a possible impending supernova explosion. But that wasn't the only surprise Betelgeuse had in store for astronomers. Recent measurements from the ALMA telescope array revealed that Betelgeuse rotates at an astonishing speed, completing one rotation roughly every 20 years. While this might sound unremarkable, for a star of Betelgeuse's size, this means its surface spins at an incredible 18,000 kilometers per hour. That's 10 times faster than the rotational speed at Earth's surface and nearly defies the laws of physics, especially for such a massive supergiant star. The basics. Let's start with the basics. There are several ways to measure the rotation of objects in the night sky. For large, nearby objects like the Sun, the Moon, or planets in our solar system, simply pointing a telescope at them and observing their features in real time is enough. The Moon, for example, has an angular diameter of about half a degree, which is easily visible to the naked eye. Jupiter's angular diameter is smaller, around 1/100th of a degree, but its features are still distinguishable with a telescope. But what about Betelgeuse, the supergiant star located only 650 light-years away? Despite its enormous size, Betelgeuse is so far from Earth that its angular diameter is 1,000 times smaller than that of Jupiter, making it appear almost completely obscured, even through our most powerful telescopes. Fortunately, there's another way to determine if a star like Betelgeuse is rotating. This method relies on the Doppler effect, which also explains the change in pitch of a siren as an ambulance passes by. When an ambulance approaches, its siren sounds higher because the sound waves reach you at a higher frequency than if it were stationary. As it moves away, the effect reverses, and the sound waves arrive at a lower frequency, making the siren sound deeper. The Doppler effect affects light waves in the same way. Light reflected off the ambulance appears slightly bluer as it approaches and slightly redder as it recedes, although this shift in color is subtle since light travels 1,000,000 times faster than sound. We'd need an impossibly fast ambulance to observe this visual Doppler effect on Earth. However, in space, such speeds are possible, and they apply to Betelgeuse as well. As a star rotates, one side of its surface moves toward us while the other side moves away. This creates a gradient in color shifts, visible through telescopes, even if the star's features are too blurred to observe directly. By analyzing the differences in the blue and red shifts, astronomers can deduce the direction and speed of a star's rotation. This was the technique astronomers used to interpret data collected by ALMA, concluding that Betelgeuse's surface rotates at a staggering 5 kilometers per second. This is remarkable, given that current models of stellar rotation suggest that 5 kilometers per second is far too fast for a red supergiant like Betelgeuse. Take our Sun as an example. Its rotational speed is roughly 2 kilometers per second, similar in range, but for an object that's 1,000 times smaller and 10 times less massive than Betelgeuse. If the Sun were to expand to the size of Betelgeuse, encompassing the inner solar system and nearing Jupiter's orbit, its rotational speed would decrease to mere meters per second to conserve angular momentum, much like an ice skater who slows down when they extend their arms. If the Sun's mass increased tenfold to match Betelgeuse, its rotation would further drop to just 0.2 meters per second. In general, the bigger and heavier a star is, the slower we expect it to rotate. But Betelgeuse defies all these expectations. So, what's going on here? Stellar cannibalism. One possible explanation for Betelgeuse's high rotational speed is that it didn't start off with so much angular momentum but gained it by devouring another star, a process known as stellar cannibalism. Stellar cannibalism occurs when a star strips layers of gas from a companion star in a binary system until only its core remains. This stolen gas brings with it much of the companion star's angular momentum, causing the original star to grow larger and spin faster than it naturally would. But is this really how Betelgeuse gained its high rotation speed? Or could something even more mysterious be happening beneath the surface? Recently, a team of researchers from Europe and China proposed that Betelgeuse's apparently extreme rotational speed might actually be an optical illusion. To understand how this is possible, let's revisit what the team measured using the Advanced Telescope Array at ALMA. Although their images of Betelgeuse were blurry, they still detected a slight red shift in light frequencies on one side of the star and a slight blue shift on the other side. The straightforward explanation for this 50-50 color shift is that Betelgeuse is rotating, with one side moving toward us and the other side moving away. However, what if this isn't the only explanation? Simulations of Betelgeuse suggest that its surface is a chaotic, turbulent place, boiling with intense heat much like water in a pot. Each of these bubbles is immense, stretching up to 100 million kilometers in diameter and covering vast areas of Betelgeuse's surface. If one of these bubbles were moving toward you, at speeds reaching 30 kilometers per second, even today's most advanced spacecraft would be unable to escape its approach. Luckily, the bubble would likely burst and collapse back before reaching you. As gas bubbles rise and fall across Betelgeuse's surface, we see patches moving toward or away from us, creating a Doppler effect that causes the light from these regions to shift to blue or red. In a recent paper, the research team proposed that Betelgeuse might not actually be rotating fast at all. Instead, they suggest that the range of light frequencies detected by ALMA could be due to turbulence on Betelgeuse's surface rather than its rotation. This could mean that astronomers mistakenly interpreted these frequency shifts as signs of rotation. But this alternative explanation introduces a question. A rotating star would produce a smooth color gradient, with blue shifted light on one side and red shifted light on the other. Meanwhile, a turbulent star would create a patchwork of blue and red areas due to rising and falling bubbles. If ALMA observed a uniform color gradient on Betelgeuse, wouldn't that rule out the patchwork explanation? In an ideal situation, yes, a smooth gradient would indicate rotation, while a patchy pattern would point to turbulence. However, Betelgeuse is so far away that ALMA's image is more of a blurry impression than a high-definition photo. Simulations of Betelgeuse's surface, factoring in the limited resolution of these observations, show that bubble patterns can appear like rotational gradients nearly 90% of the time. This means that even if ALMA's analysis was technically accurate, Betelgeuse's turbulent surface could have deceived astronomers into thinking it rotates faster than it really does. As a result, astronomers are now looking for a more definitive, higher-resolution study of Betelgeuse to distinguish between these two possibilities. The good news is that there are already better images of Betelgeuse, taken by the same telescope but with longer exposure times. The bad news is that we may have to wait a few years for these images to be fully analyzed. In the meantime, where would you place your bets? Is Betelgeuse really spinning at 5 kilometers per second after consuming its companion star? Or will the new theory that its rotational speed is an illusion be proven true? If you enjoyed today's deep dive into stars' latest innovations and want to stay updated on everything stars, sun, moon, and more, make sure to subscribe to my channel. Hit the bell icon so you never miss an episode, and join us as we explore the future of sustainable energy and cutting-edge tech. Thanks for watching, and see you in the next video.